Let's talk about the paper analyzing the role of model uncertainty for electronic health records. This paper is an important article on the concept of calibration specifically for medical usage, and we will go through it to see what it has to offer. So in the abstract part, let's read what it says. They investigate the role of model uncertainty methods in the medical domain. They use the ensemble of RNNs and various Bayesian RNNs, and then they show that population level metrics, dataset level metrics, such as arc of precision recall, ROC arc, log likelihood, etc., do not capture model uncertainty. Understanding uncertainty for individual patients or patient cohorts is an area with clear clinical impact, such as determining when a model decision is likely to be brittle. So one thing about this is that they basically analyze if, for example, if they have a model that has a very high accuracy over the entire dataset, is it compromising for a good accuracy on a specific cohort of patient while basically not being that confident about another cohort, such as male versus female, etc. They show further that the RNNs with only Bayesian embeddings can be a more efficient way to capture model uncertainty compared to ensembles, and then they analyze how model uncertainty is impacted across individual input features in patient subgroups. So this paper is overly is about understanding model uncertainty, which is very important because medical decisions has a lot to do with confidence. So we need to know when a model decision is confident and is reliable. So in the introduction section, they go over the problem of calibration, talk about the deep learning methodologies. So they mentioned that the existing state-of-the-art approaches use deep neural networks. They often make use of either a single model or an average over a small ensemble of models. And they focus on capturing the data uncertainty, meaning that they have a metric like ROC and they basically want to minimize the loss and maximize that metric over the dataset, over the entirety of the dataset. However, model uncertainty, which is inherent in fitting deep neural networks, is basically not captured within these methodologies. An example is here. When predicting patient mortality in an ICU setting, existing approaches might not be able to achieve high ROC, but might be able to achieve high ROC, but will not be able to differentiate between the different patients for whom the model is certain about the probabilistic predictions. So it means that, okay, you have a model, it predicts mortality with high accuracy, but it cannot basically provide you with a measure of confidence over patients to kind of reliably determine how confident the model is in its decisions. So in this paper, they examine the use of model uncertainty in the context of predictive medicine. Several questions occur in predictive medicine, and then they basically want to go over these questions, and these are actually important. One of the questions is, how do the realized functions in any of the approaches, such as metrics over the dataset, compare in terms of population level metric performance? So we have individual models in the ensemble, and basically we'll want to compare them. The other question is, if and how does model uncertainty assist in calibrating the predictions? How can we use that in terms of loss, perhaps? How does model uncertainty change across different patient subgroups? This is one of the sections of this paper. They go over the various uncertainty levels over patients characterized by various statistical or demographical features. How do various feature values contribute toward model uncertainty? And how does model uncertainty affect optimal decisions made under a given clinically relevant cost function? So they use Mimic3, they use the EIC with 2 publicly available EHR datasets. And they find that models within an ensemble can collectively exhibit a wide variability in predictive probabilities, which means that, okay, you have different models that in an ensemble that basically reach the same, roughly the same amount of performance metric over the entire dataset, but they are different when it comes to model uncertainty. They find that this even extends to the space of optimal decisions, which means that models with nearly equivalent metric performance on the dataset can disagree significantly on final decisions regarding the examples. And basically they transform the optimal decision into random variable. And this factor makes this transformation. So significant variability in patient-specific predictions and decisions can be an indicator of when a model decision is likely to be brittle. And they show that using a single model or an average over models can mask this information. And this motivates the use of model uncertainty. They also show that Bayesian embeddings is a more efficient way to do this. And that basically stems from the fact that you have probability distributions versus having to train m different models. So let's go over the background a little bit. So what is data uncertainty? Data uncertainty is basically uncertainty regarding a given outcome due to incomplete information. So assuming that we have the outcome y and input x in a learning scenario, we can define this function f of x in weights. W would be weights in this case, but learnable parameters w, and basically outputs the parameterization of the predictive distribution, namely the probability of outcome given the inputs and the weight. And for binary tasks, we can basically consider the Bernoulli distribution, and we can basically use this output in that to basically find out what is the distribution that the outcome is drawn from. Now when it comes to model uncertainty, we have basically a family of functions. So assuming that we are going to work with this weights, the parameters, they come from a distribution, and we can define this function here So we have this distribution over functions, and we have this function gx here. So this is a function that is formally defined, given. So when you have an input, you can formally define this gx, and then what happens is that if you give it the learnable parameters w, it's going to return lambda for you, and then you have these. So essentially, the probability of lambda given x would be the derivation of this with respect to lambda, and this is something that we have. Now we can write the probability of outcome y condition on input x as this, and then basically we can change it as lambda condition on x instead of the w. And then basically this can be rewritten as this. Now when it comes to, say, lambda, when we have different models, we would have different lambdas perhaps. And what happens here is that, okay, so we can focus on the average of lambda. That is a good indication of that is a good way of aggregating the values of lambda. But one thing that is even more important is this variance here, which is a measure of disagreement between models. So if you have multiple models and both of them achieving high accuracy over the entire data set, and then when we have a high variance of these lambdas for a certain input, what happens is that it means that there is a disagreement between the models. So this measure can be used for that. Now we can go to the concept of calibration. And regarding the concept of calibration, a model is said to be perfectly calibrated if, for all examples for which the model produces the same prediction p for some outcome, the percentage of those examples truly associated with the outcome is equal to p across all the values of p. So if a model is systemically over or underconfident, it can be difficult to make reliable use, specifically in the field of medicine. So how do we measure the calibration performance? So there is this measure called expected calibration error, which means that if you have B bins and if you have NB being the number of examples in the B, you have the accuracy and you have the confidence for the model. So the absolute difference of these two, both of them 0 to 1, can basically become aggregated and lead to the ECE value. And then we have the deep ensembles. So what is the deep ensembles metrics here? So basically there's not anything unusual. It's just you have M models, M deterministic neural networks. You train them with various random seeds, and then they basically obtain M models. So for example, when we have lambdas, you can it can lead to M lambdas here. So lambda 1, lambda 2 to lambda M. And you know, these can be seen as examples drawn from this distribution. And then they have also Bayesian RNNs. So what is Bayesian RNNs? So we have RNNs with prior distribution PW placed over the parameters. So what they do is that it allows them to express model uncertainty as uncertainty over the true values of the parameters in the model. So we have weight uncertainty here. So they basically have, so when they want to compute or basically assess P of lambda given X, they draw M samples from a single Bayesian RNN for a given example. So one thing about this is that you will see that in some of the experiments this cannot be used because they want something that, you know, models that act the same or globally rather than example-specific behavior. And in this case, for each example, we're going to sample basically M samples from a single Bayesian RNN and, you know, do that. With regards to model uncertainty, so they work with the MIMIC and EIC dataset on tasks of inpatient mortality prediction and multi-class diagnosis prediction, for which they use the clinical classification software. Now let's go over the models here. So for the models, they have, so what they do is that, so for each one of these, for EICU and MIMIC, we have timeline for patients. So what they do is that they take patient features, dynamic features, and then they take static features and embed and aggregate them, and then basically they form sequences of feature representations composed of global contextual features such as gender and age and other dynamic features, and then they feed it to LSTM and then output hidden layers and affine layers for the output. Namely, they go with one-day blocks. So this work focuses on addressing the model uncertainty. So that's important. So the final time-step output of the LSTM would be basically the parameterization lambda for predictive distribution of probability of outcome given input and weights. Now let's go over the choice of uncertainty models. So for the Bayesian RNN, so for the case of ensemble, they basically train M replicas. For the case of Bayesian, what they do is that they have this Bayesian RNN with, so they take the variational inference approach, and what they do is that they use this multiplication rule, so the probability distribution, so they use basically factorized weight posteriors. So if you have weights, and so for each weight group, they have, so these weight groups are represented by normal distributions with parameterization theta, and then they use the multiplication rule to obtain the Q of weights conditioned in theta. And for the loss, we're going to have something like this, which is the KL divergence between the probability distribution of weights conditioned on the parameterization and the probability distribution of weights conditioned on outcome and inputs, which is going to be simplified to this. Now, why is it the case? So if we take the KL divergence, the initial KL divergence, but if we expand the equation, we'll have something like this. Now, if we take the probability distribution of weights conditioned on outcome and inputs, we can basically use the Bayes rule and get to this. And yeah, we can basically transform it into itself. And we will ignore this part because it's not relevant to the loss. And we will basically retain this part. So what we do is we retain this part here and we rewrite the equation. So we have the KL divergence of these two. It will be rewritten as this. And then this will amount to this KL divergence minus the average of this function over the distribution Q. So basically we have the approximate weight posterior and we have the true but unknown posterior. So we are basically measuring some measure of difference in distance between the two. Now what happens to the optimal decisions if we try to think of it this way? So first of all, let's look at this equation. So if L is going to be the loss of predicting J for an example when the true class for the example is K, we can see that we have a loss like this, which means over all the true classes and all the predicted classes, if we have RJs being the region of the decision of assigning J to an example X, we can have this here, and then this aggregation will give us the final expected loss. And designing an elaborate decision cost function for clinical application, they mentioned it's a good thing, but it requires a vast amount of domain knowledge. So it's not the focus of this paper, one would say. So for example, consider the case of a binary prediction task. We will have, so this is going to be an indicator function, and these are going to be m different ensembles. In this case, consider the ensemble models. So we can have this phi here, which is a percentage of model agreement on the decisions. So you have m models, you average over them, and this is binary value, either 1 or 0. And if you take d, that is basically drawn from this Bernoulli distribution with the percentage of model agreement, that would give us a sense of how confident the models are on the decision. So far we talked about the methodology and the contributions. For the experiments, they performed 4 sets of experiments. They worked with individual RNN models in terms of predictive metrics. They demonstrated the importance of quantifying uncertainty in predictive medicine. They examined multiple variants of Bayesian RNNs to understand where uncertainty in the model matters most, and compare them with the deterministic ensemble counterpart. And then they used the deterministic RNN ensemble to examine uncertainty across different patient subgroups and cohorts. And finally, they analyzed the Bayesian RNN with embedding distribution to examine uncertainty across individual features. Now, don't worry about these descriptions, let's go forward. So knowing that models in our sample are well calibrated and effectively equivalent in terms of performance, we turn to prediction for individual examples. And then they find that there is a wide variability in predicted Bernoulli probabilities for some patients. So, what does this mean? So, ignoring the variance over lambda, basically, if you want to ignore it, it's not going to be possible to distinguish between data uncertainty and model uncertainty. One figure that is worth noting is here. So this is the plot of mean versus the standard deviation of the predictive uncertainty distributions, the probability of lambda condition on X, of the deterministic ensemble for positive and negative patients in the validation set. And then they find that the standard deviations, there's no simple linear relationship between that and the mean. And they note that overall the variance of distributions are generally lower than of the value for a Bernoulli distribution's variance curve. Another interesting observation is here, which is the histogram of standard deviations for all patients in the test set. So one thing that they can see is that so they have the same setup for top and above. So they have the standard deviation, so they have negative and positive patients and examples. This shows that there's a wide variability in predictive probabilities for some patients, and that negative patients have less variability on average. Because if you can look at this distribution here for both standard deviation and max mean, we can see more of a Dirac delta-like function. They have basically different variants of Bayesian RNNs and deterministic RNN samples. Bayesian embedding means an RNN in which the embedding parameters are stochastic, output, hidden and output, and RNN hidden and output, and full Bayesian. So these are the different variants of the Bayesian models they have. So the result of their experiments also show that the Bayesian model is more efficient to train rather than having to train M models, because then we would have M times around 6 million parameters. But with Bayesian models we can have less than that, a lot less than that, because M times more efficient in terms of storage space at least. Now they go over the patient subgroup analysis. So they split the validation set into subgroups, basically different cohorts, demographic characteristics. So first they go over the male versus female genders. And then, for example, they show and realize that there is a negative correlation between the arc of precision area under curve of the precision recall for male and female. So it kind of means that models decide to kind of compromise the accuracy on one of them in order to boost the performance on the other. And they focus on the RNN ensemble here. So the reason why is that they want something that exhibits the same global behavior and not sampling 200 weights for each prediction each example separately. And essentially that is what we do. So these findings would imply that random model variations, so slight changes, say in the initial conditions and initial weights, can cause unintentional harm to certain patient populations while maintaining a good accuracy and good performance metric over the entire dataset. So this aggregation would mask out these alterations. And then they go over the embedding uncertainty analysis. This part is not really novel, and then what they basically go over the words in the medical texts. They find the lowest uncertainty and highest uncertainty. Then they find that there is a non-linear relationship between the number of times the word has been seen with the entropy that it exhibits, and that would basically conclude the paper here. It is important because calibration is a very thriving field at the moment, and specifically it is very important for the medical applications.